of using MapReduce for index construction, distributed index construction, also computing PageRank on a large scale basis. Okay, that's first part. And if I get done with that, then I will shift to the next topic, which is clustering, clustering of text results. Okay, so that's the agenda for this. Questions before I start? Okay, so as we left last time, as a laboratory last time I showed this, I'm going to go over this again. So the idea is to kind of give a brief background. MapReduce is a particular way of programming which will allow you to use large numbers of cheap machines, essentially arranged in the server farms. And the idea is that you have both a map part and a reduce part. And you can think of the computation itself in terms of an abstract data type of keywords and their values. Okay, so the map part starts with a bunch of keywords and values. Not keys and values, not keywords, keys and values. And essentially it maps them into a set of keys and different values. So it does some computation and computes new values. Okay, and then at this point of time, these intermediate key value pairs are reduced by first of all grouping them such that if keys of the same type, all their values are combined together, are grouped together. Okay, and then the reduction basically would do some computation over the group, such as adding them up, such as unioning them, such as doing some other computation. Okay, so the interesting question is, if what you need to do can be written as a map task followed by a reduce task, and the number of mappings depends on the size of the input, and the number of reduction also obviously is a little less, but it depends on the size of the input. Then in essence what you can do is, if you were to write that in the MapReduce form, if you can write your computation in MapReduce form, then there is infrastructure which will misusing the term map that computation onto individual CPUs at the runtime. Okay, and so that's basically what the architecture, MapReduce architecture does for you. So you, the programmer, needs to ask yourself, anything I need to do, can I write it in this MapReduce form? That's the question. Some are easy to see, some are harder to see. And much of what you need to do is, it's like you do have this huge big hammer. It's basically this humongous number of servers, that's cheap CPUs sitting there, and there is an infrastructure which will take any program written in the MapReduce form and schedule them onto these CPUs. I'll tell you a little bit more about those details. But eventually what this means is, this is a kind of lecture which is telling you that if you were to write what you want to do in assembly language programming, here is a CPU, Intel CPU, which will run this assembly language program for you. That's what this lecture is saying. But the rest of your life, really, you would have to write the assembly language programs. Whatever computation you have to write it as an assembly language program. And similarly for you too, most of what you will need to do if you want to use a MapReduce architecture is to write your computation as a MapReduce computation. Okay, so you have thought of lots and lots of different higher level languages. You have to write something in C. A little later you have to write it in Lisp. And some of you may have written your computations in Prolog. How many of you have written in Prolog? None, or at least one. Okay, so these are completely different kinds of programming languages, and you have a computation and you're able to specify it in a completely different programming language and a completely different programming paradigm. Right? So you have one more here. And the question is, this has some advantages. It's not meant to be a highly general purpose, but it is extremely good for some style of tasks where the parallelism is based on the size of the input. Okay? Anyway, so the keyword and the key and value is the abstract data type that you want to think in terms of. Okay, so you reduce these into keys and values, and then these are output. Okay, that's the output of the computation. So you have to think of, can I write what I want to do in this form? And I'll give you some examples today. But then, anytime you want to do something else on this kind of an architecture, you need to think about how to write your computations. And really the best way to get used to MapReduce is write programs for MapReduce. So if you have access, you can install Hadoop and then try to write programs for it. And it'll simulate CPUs on your single machine. Okay, so input is of course a set of key value pairs. User supplies 2 functions. So you only have to supply these 2 functions. A map function which takes keywords and values and gives you a list of new keywords and values. How you go from here to here, it's your body of the program. You write it. Okay? And then a reduce function which takes keyword and a list of values corresponding to that keyword and then gives some sort of a reduced representation of all those values. A simple thing could be adding them up. Another thing could be summing them, maybe taking the max of them, or any arbitrary computation which somehow is a function of these list of values. Okay? Now, so this basically, so you went from KV to K1V1 and then K1V1 to V2. Okay, so these are the intermediate key value pairs. And everything is key value pairs. Okay, so the output is the K1, V2 pairs. Okay, that's what you would say. Okay, so here is a pseudocode definition, description of counting the words in a document, counting the occurrences of different words in documents. Okay, so this map key value, the first ball it does basically is for each word W, then you emit W1. So this word occurred once. So the value is 1. W is the key, value is 1. Okay? And now, so basically after this map, so this map will be subjected, large number of documents you have, they are going to be given, pieces of these will be given to these mapper routines. The interesting part about this map routine is each instance of this map routine might be running parallelly on a different CPU. Okay, so if you have, let's say, 1,000,000 documents, you might basically give 100 documents to each machine. And each machine will then emit these W1 pairs. I mean, the key and each word and that it occurs. Each word and that it occurs. That's all it does. It's like almost trivial thing to do. Okay, but by the end of this, of all the map phases, you essentially have a whole bunch of the words that occur. Okay, but they're in the key value format, right? Key is W and value is 1. Okay, now all you need to do is you want to compute the number of times each word occurs. Okay, so in the reduce phase, you need to take all the W's, all the So notice that in the document P1, here is the CPU 1, which may have put raw 1, and it also has put raw 1 little later because it found one more raw. Okay, and then here's another CPU. It too put raw 1, raw 1. And so in the reduction phase, I basically have to say raw 1, 1, 1, 1. That's my list. Okay? What?
There is no dominant
In this particular case, I'm only counting the number of words. Number of occurrences. In this case, actually, I'm just counting the number of occurrences of a word in a single document. Okay? So then basically what I can do is, I have this 1, 1, 1s, and then all I need to do is I need to do, so remember that we talked about the fact that reduction takes the key and the list of values and then gives out a value. Okay, which in this particular case would be just addition. Okay, yes. Yeah.
This thing will happen, will this happen in
or by the combiner?
This is combiner, you could say. I mean, so it's a map and reduce, essentially. So in the phase where the grouping occurs, that's where this is occurring. Okay. Okay. So you have, in this case, you just added up the numbers. So it's the simplest MapReduce program. We'll see one more for indexing later. Okay. So how this kind of a program gets, if I give you this in MapReduce, how does this get scheduled onto the CPUs? So the idea is the available CPUs are known only at the runtime. Okay, and the operating system for MapReduce, Hadoop is the operating system for MapReduce, for example. It essentially, at the runtime, decides how many, processors to, how many CPUs to give to the map phase, how many CPUs to give for the reduce phase. Okay. So here is basically when you give the user program. First of all, you have to realize that one of the things we'll keep looking at this is, notice that there should be a lot of data so that each CPU gets a piece of it. Okay, if it was a large single document, which was my problem, then I had to take the first chunk of the document, give it to one CPU, second chunk for CPU, another CPU, and so on. If I have a large number of documents, then presumably I will give some number of documents to the first one, some other number of documents to the second one, and so on. Okay. The interesting thing is that, so you need to think of how to split the data in such a way that each of the pieces of the input data are handled by a separate input machine, CPU. Okay. This actually is very easy in this case, and it's also easy for the indexing case. But when we start talking about how to compute PageRank, it's not as obvious. So I'll give you an example there that will make you realize that sometimes you have to think slightly in a non-trivial direction to find out how to fit your computation into the MapReduce framework. You do this all the time. Whenever you have a computation to be done and you have a crazy language that you want to write this into, you need to figure out what's the best way to write what you want to do into that language. Okay, so it's just in this case, it's this scenario. So you have split the data into multiple splits, 0, 1, 2, 3, etc. Okay, and then this user program essentially, as the user program forks into multiple processes, these are the map workers, these are the reduce worker processes, and this is the master process. Now each process can be run on a separate CPU. Okay, the master process basically assigns each one of so it does basically the mapping assignment and the reduction assignment. So which CPU does which part of the input. This is all done behind the scenes, so your life is much simpler. You don't need to know who is doing what. Okay, so it's assigning the workers. It also is assigning the reducers. Okay, and then the workers then read the splits, the splits that have been assigned to them. Okay, and then do the local writes onto their own CPUs. Basically, it's like this part. This read is over the distributed file system. Remember last time we talked about distributed file system? So this read is over the distributed file system. This write is local write. Okay, and then this has to be done remote read again because the reducers are on a different part. Okay, you may want to reduce the latency. You might want to throw in workers, the reduction workers to be closer to the map workers for individual pieces of splits that are local. Okay, that basically work on each other. Okay, that is something that the master can do, but you don't need to do any of this. This is all, if you have a better implementation of MapReduce versus a worse implementation, that's the difference. Okay. So then you have the workers, and then the workers will send out the writes again back into the distributed file system. Okay. So that's basically what is happening below you. If you were to write your computation in that MapReduce format, then this is how it gets implemented, and then you can take, irrespective, you don't really care about how large your data is. Somebody is splitting it and then combining it and giving you the results. That's what is the point. Okay. So then all you need to do is think of how to write your computation. as a MapReduce. Okay. So my understanding is that in most of these companies, if you join, the first 2 days, they will basically tell you the libraries for using the MapReduce. Okay? And once you do that, then essentially any computation you write, you have the entire server farm at your fingertips. Okay? So this is basically saying what I've already said, that input and output, final output are stored on the distributed file system. Scheduler tries to schedule map tasks close to the physical storage location of the input data so that there will be less transmission. But that's not something that you have to worry about. Intermediate results are stored on the local file system of the map tasks. Output is often input to another MapReduce. Okay, so sometimes the MapReduces could be pipeline. So your single computation might have multiple MapReduce phases. It doesn't have to be just one map and one reduce. Okay. So now coordination basically is, this is talking about how the processes coordinate. This you don't need to again care about it. It's just figuring out once how operating system works, and then you just use it. Okay. So in this case, it's talking about how the tasks get scheduled to the machines that get available, and when the map task completes, then the CPU has to send to the master the location and sizes of the key value, the intermediate key value splits it has produced, and where they are. Okay, that is then has to be sent to the reducer, which works on that part of the data. Okay, that's what is basically being said. Okay, and every once in a while, the master has to check to see if the workers are alive, or if they have signed off and gone off. Okay. Now that gets us to the interesting part, which is what if the signed off and gone off? There's so many CPUs working on your computation. If one of the CPUs dies, what do you do? Remember, the whole point of this architecture is it's fault tolerant. Individual CPUs can be dying, and you still don't have to restart the entire computation most of the time. So there are different kinds of failures. If a map worker fails, then the specific tasks that are completed are in progress at that worker. Remember, master remembers which parts of the map tasks are done by which CPU. When it pings that CPU doesn't get back, then it assumes it's dead, and then essentially it just has to give that task to somebody else. Okay, a new worker. Okay, so reduced workers will then be notified that their map will now be coming from the map task input will be coming from a different CPU. Okay, if the reduced workers fail, then anything that's currently in progress is redone again. It's reset right. If the master fails, then the entire task is abandoned and you restart all over. There are different kinds of failures at least. Right? That's basically what, again, it's just the obvious thing is you start buying really fault-tolerant systems. We are buying cheap systems that are reasonable, and you are dealing with the failure. You're assuming that failure will happen. And since the computation has so much parallelism in the map level as well as the reduced level, you can handle the failures without having to restart all over again. Yeah.
That point, reduced workers are notified when task is scheduled on another worker.
Mm-hmm.
It's been a confusion. So
Another map worker, basically. So the one map worker died.
Basically, reduced worker will get a task to run only when master says you have an input ready, right?
Yeah.
So when the input is ready, reducer will just go ahead and process it.
That's true. Actually, I think if as long as reduced worker is just told, it depends on, it's possible that in some cases, again, I'm guessing as much as you are, in some cases, the master might already have told the reducer, at the same time it is picking the map, that when the map guy starts putting input and output, it would be in this position. So you can start working on the input in a asynchronous fashion. Okay? If that happens, then you need to be retold. You see what I'm saying? Yes?
Can the master switch nodes between being a map or reduce dynamically, or is it just...
No, for a particular computation, you are either a map or a reduce, but then for the next computation, there are completely identical nodes. So when you become available, you go to the pool of available CPUs. And the next time, there is no separate characteristic for the map worker and a reduce worker.
As soon as you finish your current task,
Then you become free. And when you become free, you go to the pool of free machines. Total commodity, basically, right? And it's fungible commodities. Okay. And then in terms of map and reduce jobs, the idea is that the number of map jobs, so if there are M map tasks and R reduced tasks, then M and R are much larger than the number of nodes in the cluster. Basically, the idea being multiple map tasks might be given to the same CPU. Okay. One DFS chunk per map is common. You know, the way you split the map task is basically, remember the file system itself is stored as chunks. And so, you know, the size of the split is the size of the chunk. Okay. And what else do I want to say? One thing is that normally for most reasonable computations, the reduced tasks are fewer in number than the map tasks. That's just the way the computations tend to occur. Okay. And so there will be fewer CPUs that would be needed for the reduced task than for doing the map task. Okay. Okay, so that's basically the background on MapReduce, how it gets implemented behind the scenes. Okay, and if you're interested, obviously, as I said, the two people who worked on this, the Google, which is the first one which actually did this, is Jeff Dean and Sanjay Kamawat. And you know, here is a paper that you can look at for more details. And then this is just about the Google file system, which is the distributed file system with chunks and so on. If you are like an operating systems person, you know, you will enjoy this. Okay. For the rest of us, what matters more is this is the computation that's being supported. So whatever I want to do, convert it into something that's supported. That's basically what you want to do. Okay. So first thing I want to do now is talk about distributed indexing. Okay. So remember, the first stage of search computation is computing is huge inverted index. Okay, how do I do it in a MapReduce form? Basically, that's what I'm going to talk about right now. Okay, so the idea is that you will split the computation of inverted index. Remember, inverted index will be, there's a huge number of documents. From them you compute the occurrence list, and then you reduce the occurrence list. You kind of unify all the occurrence lists. So in this case, you would say raw one in each of the documents. You know, in document, in a particular document raw is occurring, another particular document raw is occurring, and then you want to kind of combine these occurrences and then invert them to get the inverted index. Okay. So you have two phases. One is parsing of the documents to get the word occurrences, and the reducing converts the occurrences into postings. Okay. And so that's your map and reduce. So this is your map part and this is your reduce part. This happens, this is a computation that almost is made for MapReduce. There are other computations that are not, you know, as obviously made for MapReduce, and so you have to think of how to make it into a MapReduce task. Okay. So now each split, again, remember you need to split the input. The split is a set of documents. Okay. So what you wind up doing is basically, so you have a situation like this. So all the documents essentially are made into splits. Okay, and each split is being worked on by a different parser process. Each parser sends out occurrence lists, which are then put into these lists we'll talk about in a minute, and then the inverter processes will work on these to compute the inverted index postings. Okay, let me give you more details on this. So the parser basically, the master assigns a split to an ideal parser machine. It's a map machine in this case. The parser reads the document at a time and emits the term document pairs. Term occurring in the document. Term occurring in the document. Parser writes the space into J term partitions. It's basically these partitions. Okay. For each range of terms, first letters. So basically, in this case, I wrote the word occurrences into A to F bucket, G to P bucket, Q to Z bucket. Okay, all the words that start with a letter between A and F will get thrown into this. All the words that start with letters G to P will get thrown into this. Okay? And notice that same thing all other parsers do too. Okay? Now having done this, now the inverter, what it needs to do is it needs to take all the A to F buckets of all the machines and then invert them. Okay? And so you only need as many inverters as there are these partitions. So if I put J equal to 3, that means I only need three inverters. Right? Okay? So obviously you might want a much larger, if you want to use more parallels. Okay, so in this case, all the A to Fs are taken, and you got to, so inverter collects all the term document pairs for one term partition, and then sorts them. That's where you first sort it. The mapper doesn't sort. The inverter sorts, and then writes it into the postings list. Okay, so by this time, you have alphabetically sorted list of words and which documents they occur in, which is your inverted index. Okay? So here is a scenario where you actually did inverted index construction using MapReduce. And it turns out to be, this is about the only way, in this case, essentially, the postings are now, put again to A to F, G to P, and Q to Z. And this is again, this whole thing is in a distributed file system. The inverted index itself is in a distributed file system. So they may not fit on any single CPU's memory, CPU's disk or memory. Okay. So that's how you do MapReduce for indexing.
So basically, the reduce case is just sorting these things. I mean,
that's all you have, right? In the inverted index. It's a simple task, but it's done for a huge number of documents.
So isn't parsing intensive task?
What do you mean? I don't understand.
Like if you're
parsing is picking words. How intensive can it get?
So,
Not as bad as sorting.
but in parsing, you are determining which document this term belongs to.
Yeah.
So,
no, when you're reading it, you take a document and you are setting set document to be D1 and keep setting out words. D1, W1, D1, W2, D1, W3, D1, W1 again. Right? I mean, it may well be that you would like to think that the parsers are doing more work than inverters here, but that's okay, I don't care. They're both doing much less than really complex computations. Each of them, they're basically doing very simple computations. The complexity comes in the size of the input, not in terms of individual computations. Okay, and that's what MapReduce is tailor-made for. Yes?
I was kind of thinking that you said this problem is as if it is made for parsers and,
MapReduce, yes.
But it looks like the same parser, when it's done parsing, can take up the work of inverting it.
No, again, no. It's not that. Parser and a parser process might be instantiated on you or him. And then if you got instantiated as a parser now, when you become free, you may be reinstantiated again as a parser or a reducer. Or you may not even be reinstantiated in this process at all. Because the entire server farm is available, and so somebody else has a different MapReduce task for computing the PageRank, and you may get assigned to them.
No, but the way I look at it is there is a main program which has two functions, one is parsing, one is inverting. So the same processor can do both as soon as the parser gets over, right?
Yeah, the parsers are, the CPUs are general purpose. But the issue is that the structure of the computation is there's a map followed by reduce. And the map workers are the parser workers here, the reduce workers are the inverter workers.
Did this happen parallelly?
What?
Did this happen parallelly or sequentially? Parsing is when inverting is passed.
So that's a good question. So you can, all the parsing can happen parallelly. Okay? And then think about what happens for the inversion. If you are not waiting, there are some cases you want to explain it to the rest of the class? That's fine though. I think you seem to know something more. What I was trying to say is that the question was whether the parser followed by, we do know for sure that parsing is all parallel. We do know for sure that inversion is all parallel. The question of whether these have to be strictly sequential or not, that depends on the computation. Okay. The worst case assumption is that they have to be sequential. That means you have to have the parsing get done before the inversion starts working. Yeah.
The inverter will have term and list of documents.
Yes, that's what it does. Right? It's getting documented terms, and then it outputs term and the list of documents. So it changes both the keyword and the values. So think of this in terms of keyword values as the computation. Yes?
So the parsing and inverter thing going on sequentially or parallelly, we define it, or the operating system defines it?
My understanding is map and reduce, normally reduce is supposed to be after map. Okay.
In this case, actually, it's much more easier because otherwise you would have to sort every time.
Exactly.
But in some cases, parallelism would be useful, like counting and something like that.
I mean, so that would still be any time computation. That means the final answer will still not be over until the entire. So the difference is whether inversion can happen concurrently with parsing. Eventually, the last step of inversion has to happen after the last step of mapping. Right? The question is whether there is going to be concurrency or not. You can allow concurrency, but the result is output only when the entire map is over. Okay. Again, the problem with this is also that most of these except Hadoop are proprietary, and I don't know how they actually implement this. Okay, and this is actually the first time I'm teaching this in the class. In the past, I would just say there's MapReduce, you can use it. I actually think it will be more interesting for you to write your own computations in MapReduce. But it's a situation where it's become common enough that you may as well want to think about how to write your computations in this form, because that's what is supported. And in fact, there are papers that get published where much of the paper is how did we do this computation, this clustering task as a MapReduce computation. So, and you barely ever get a paper for saying, how did I write my program in Prolog? Nobody cares because you're supposed to do it yourself, But MapReduce is novel enough that, at least as of 2 years back, they were still publishing papers where if you found some interesting way of converting your computation into MapReduce, that's still worthwhile, telling you. Okay, now notice that again, this is the entire, so that's regarding the computation. This is actually a different point. This has nothing to do with MapReduce per se, but this is something that came up a couple of times in the class. The index, even as you completed the index is already obsolete. Because new files came into being, new URLs came into being, old URLs stopped becoming available. So what do? You have to reconstruct index every once in a while. But what you might do typically, one simple idea, there are obvious middle grounds between the simple idea and so the one extreme idea is as soon as you're done computing the index, recompute the index, right? The other idea is compute the index and do the following thing, which is essentially you have computed the index, and as you get new, so you maintain a big main index, okay, which is what you just computed, and any of the new documents that the crawler found since the past index has been computed, they go into an auxiliary index. Okay, and then of course you have to search across both main and the auxiliary indexes. Okay, when you're doing the actual results. Okay, now the question of course is every once in a while you have to merge this auxiliary one back into the main one, because so that you have one single phase. And the question is how often do you want to do it? It's up to you. I mean, you the search. Okay, and then somebody actually was asking about this. What happens if at the end of last class somebody was asking this. what happens if a file got removed from the last time you crawled? This time you crawled, that file doesn't exist anymore. Okay. First of all, search engines do give links, and when you click on that link, it doesn't exist. I mean, it happens all the time. Okay. But if you actually want to keep track of, sometimes they might realize that the file doesn't exist, and the next time the entire master index is constructed, that file's URL will go away. But in between, you could basically, for the deleted documents, you can put basically, some sort of a flag saying this is deleted. And then, while you are about to put out the results, if any of the results happen to have a 0 in that flag, even if it is number 1 result, you don't show it. That's one idea. Okay. So notice that this is just one simple extreme, and not ever changing every day is changing every second is another simple extreme, and there are in betweens. Okay. So again, as I said, these are engineering. This part of the lecture is really engineering search engines, and so it's engineering. It's not. There is no proof that one way is better than another way. I mean, there are trade-offs for different ways. Okay. So, yeah.
If you just keep the flag of deletion, so that might in the end it eventually would result. It would affect that our SVD or whatever the alert of the tree.
Oh yeah, lots and lots of things get affected, of course. But again, in fact, keep that in mind. We'll get to another point hopefully soon, where we will do things for efficiency's sake, which actually change the nature of the computation we are supposed to be doing. Just keep this in mind, when we talk about dangling nodes. Okay, but that's basically what you want to take. Okay, so the next thing I want to talk about, in fact, the last thing on the engineering issues I want to talk about is computation of PageRank. Especially if you're doing it at the global level. Remember that you could do link analysis either at the query time or before query. Okay, global versus query specific. Obviously you know that right now it's computed in query independent fashion beforehand. To the extent PageRank is being used at all, which I have no clue whether they're really using it or not, but they do compute it beforehand. So the question could be, how would you power iterate on a web scale matrix? Computation of PageRank is nothing but power iteration on the matrix. Okay, except this matrix is not a 5 by 5 matrix, not a 10 by 10 matrix. It's a 8 billion by 8 billion, or maybe even larger matrix. How exactly do you do power iteration on that? And furthermore, this is also a good case in thinking of using, to the extent your hammer is MapReduce. That's what you have to do anything faster. How would I compute PageRank in such a way that piece of the action is done by different CPUs? Okay, how do I convert power iteration such that whole bunch of CPUs can take part in them? That's the question. And upfront, it's, depending on the frame of mind you're coming into this task, upfront it may not be obvious as to how to split it. Okay. So let's look at the big issue, of course, is the link matrix, right? Once you have the link matrix, then you can do everything, essentially. Okay. Now, the good thing about the link matrix is it's sparse. Okay. Actually, it's a very interesting point that the 1-0 matrix, the adjacency matrix, is for sure sparse. Right? Do you know what sparse means? Sparse means it's a matrix where most of the entries are 0. There are very, very few, a small fraction of the entries are non-zero. Okay? In an adjacency matrix, most of the entries are 0 unless you are in one of these scenarios where you have completely connected them. Okay? So now the question then is PageRank matrix sparse? Is PageRank matrix sparse? Is M star sparse? No. So, if the 0th order mistake anybody can make is to assume that you will directly handle M star during computation. Because if you do that, you no longer have sparsity and you're dead on arrival. What you should do instead is to write your program in such a way that this is what is happening here in all these steps. You start with the link matrix and during the iteration compute the entries as on demand. Do you understand what I'm saying? So the M star came from the link matrix. Okay, so you only keep the link matrix and compute M star, the part of M star you want, and as and when you need it. The link matrix is sparse, M star is not. Okay, again, this is something that it's not worth spending time on in a conceptual sense. What's the big difference? And there's a link matrix, there is the stochastic matrix. But it makes all the difference as to whether your program will actually run or not, because one is non-sparse, one is sparse. Okay, so yeah, this is Bill Gates is moving on. So if you have a sparse matrix, like the link matrix, this is how you would essentially, this is one data structure you can use to represent that matrix. Okay, so imagine that all the nodes are given unique IDs, all the URLs are given with unique integer IDs. Okay, I need to stop this. So I'm not even sure that I can stop. Does anybody remember? Oh, this was like a slideshow. Don't. I didn't even rehearse, believe me. Actually, this is. I know why it is. Because this comes from a talk given by Tahir Haviliwala, who actually, came up with this idea for computing PageRank efficiently. And so presumably he did rehearse. And so it's using his rehearsal timings. But anyway, so you have this already. This is a huge improvement over full M star. So you only keep the link matrix. So here all you're saying is this is my source node, and the source node has the out degree 4, that means there are 4 links it is pointing to, and the nodes it's pointing to are 12, 26, 58, and 94. Okay, and then similarly 1 has an out degree 3, and it's pointing to 5, 56, 69, 2 is out degree 5, 1, 9, 10. This is your matrix representation. And if you have this information, you can compute PageRank. Right? Okay, so basically all this is doing, and you can look at it carefully once you leave the class, you essentially can see that these steps are computing the M star entries, and they're doing power iteration. Okay, because after all, if you know the out degree, then you know since the out degree is 4, then the probability is 1/4, 1/4, 1/4, 1/4. Now out degree is 5 here, so 1/5, 1/5, 1/5, 1/5. And then if I give you a C, then using that, you do C times and 1 minus C times. Okay. This is a simple idea that you can do on a single CPU. Okay. My question now is, if I have many CPUs, how can I distribute this computation on many CPUs? The first question for MapReduce is, how do I split? How do I split this matrix? Now you can say one idea is I split up to 0, 1, etc. up to 100. That's one part. 101 to 200, another part. 201 to 300, that's another part. Now, if you split that way, think about this. If you split that way, it does not give you MapReduce structure. But then you split the other way. What's the other way? You essentially say that you split this matrix into, let's say, 10 matrices. Okay? In the first one, the out degree is only taken for nodes between 1 to 100. The second one, 100, 1 to 200. The third one, 201 to 300. So all of them would have every one of the nodes as the beginning nodes, but the destination will only be in a particular bucket. Now both of them are splitting. One actually works for MapReduce, one doesn't. And this is what I was saying in terms of, sometimes it's not trivial as to how to convert your approach into something that will work with MapReduce. Okay, in this case, even if you, in fact, this particular thing is being taken from a paper on efficient computation on PageRank that I have mentioned, that actually is available from the readings list. And it was actually just done on a single CPU. It wasn't done on MapReduce, because at that time, this guy was a grad student. I didn't have MapReduce architecture. But even if you don't have MapReduce architecture, it's still worthwhile splitting the file, because if the entire file doesn't split in the memory or disk, then you need to essentially split it in such a way that parts of it split in the main memory at a time, such that you don't keep going back and forth between main memory and disk. So if you read this paper, you know, all the arguments as to why he is doing this, okay, which is basically I split this into, you know, bucket 0 to 31, bucket 32 to 63, bucket 64 to 95. And so basically this, you know, so for example, 0 going to 12, 26, 58, 94, in the first bucket only 12 or 26 are shown. In the second bucket 58 is shown, the third bucket 94 is shown. Okay, and he argues that the reason for this is basically because you don't have to go back into, you know, each of these, you split it into the number of blocks such that each block split, fits in a main memory. That way you don't have to thrash between main memory and disk. Okay, but the same argument for MapReduce too. It's split, you know, it can be assigned to individual, CPUs. Okay, so once you split this, then here is a block-based PageRank algorithm, which essentially computes both over individual buckets and merges them. I won't go into the details, you know, it's a pseudocode, you should be able to do this. Okay, and this way, each iteration involves a map, each iteration involves working on each of the buckets and combining the results. Okay? And it turns out that, you know, even at that time, this is much better, significantly better in terms of runtime. Okay? And then it also, this one can actually be used for implementation on a MapReduce application. Okay? So the point that I want you to remember, at least, you know, you should look at this code, this, you know, to make sure that you agree that the blocks are being used correctly. Okay? Before that, you should actually look at this to make sure that when there is single block, you are computing the PageRank correctly. Okay? And most importantly, I want you to understand that the way you are splitting the linked matrix into multiple splits. And you could have done it in different ways, and this way is actually better. Okay? Now, a couple of other things about PageRank computation. Again, this is from this particular experiment when it was done on Stanford web base, which was a publicly available web base. I believe it's still available right now. You can actually play with it. It used to have 25 million pages. Okay, which is still better than 300 by 300 matrices that you play with normally. Okay, you have if you have 25 million pages and 81 million apparently URLs that are listed, okay, notice that you should understand that 81 is bigger than 25. That's okay, because each page might be pointing to pages that don't actually occur in the current web page. If you have the entire web, then this number cannot be bigger than this. But if you take a piece of the web, then there may be more URLs that are going out than you have. You know, some of the URLs are just going out of the web page. Okay, so here's the interesting question. Must I start with all the 25 million pages? So if I do 25 million pages, then basically this one has 0, etc., all the way up to 25 million. And for each of those pages, the outlinks. Okay, can I do some approximations to improve performance even more? Okay, there was no approximation in what I did here. This is just efficient computation. You know, the PageRank you get by doing it block-based is the same as PageRank you would get if you just directly used the single matrix. There's no approximation. The only difference is you realize that disk seek is much, much higher than the main memory access. Okay. Now we'll actually be ready to do some approximations. Okay. So one idea that they talk about, it's actually quite interesting, and that sort of goes back to, and I'm no longer, if I do this, then I'm no longer really computing PageRank. Okay, but I'll be computing something that's faster to compute. Now you might say, well, if all you wanted to do is compute something that's faster to compute, why not compute 1 plus 1, right? But that's too far an approximation. Okay, so what we will do is essentially, what he is suggesting to do is you remove the dangling nodes. Basically, dangling nodes are pages which have no children, which have no outgoing links. Remove them first. And when you remove them, then there may be other pages in the web page now which become childrenless because these other guys are gone. Remove them too.
But you will lose everybody if you get removed.
No, you don't. No, you don't. Because, so think about this. A, B, C, okay, and D, and E, okay. A, B, C, and D, E. So I'll first remove E, then I can remove D. I still have this. Okay, essentially I will have a connected component, hopefully a connected component left. Actually, this does not necessarily mean that I'll have a connected component. I could have had my entire graph as this plus another copy of this. Right, in which case, while I'm removing this, then I will also remove this, and I'll have one component here left, one component here left. Okay, it'll still be like a normal PageRank matrix, beginning of the PageRank matrix, from which you still have to do your irreducibility, which means you should add a weak link from any page to any page in the remaining part. Okay, so his worry is unfounded. Removing danglers will not completely make it, go to 0. Okay, and these numbers are actually telling us a nice story that apparently he started with 25 million pages with 91 million URLs, and after these 2 prune iterations, that means remove all the dangling nodes and remove again all the dangling nodes, he got down to 19 million nodes. He was saying billion and above, I'm dead anyway, but that's a different story. But at least he did reduce the size of the graph significantly. So now if you compute PageRank on this, you're computing it on a much smaller matrix. Now, what's wrong with this picture? What happened to the guys who you removed? So first of all, here is an interesting question. In this graph, who is the most important guy? What? Why A? A is 40, B is going to C, E. And I removed it. I removed all the important nodes to some extent. So what I am removing actually, does it really make sense to remove dangling nodes? Are they somehow the less important nodes so that you can ignore them? No. In fact, the ones you are removing are likely to be more important than typical. However, what you can do essentially is you remove them, compute PageRank on this. Okay? If you compute PageRank on this, you'll sort of get 1/3, 1/3, 1/3. Okay? And then I can essentially assume that this is, if in fact, after I remove these nodes, the remaining graph is large enough, then in essence, adding a few nodes back should not change the graph too much. Okay, so then what I will assume is I'll assume that the steady state probabilities I computed for ABC are remaining same even when I threw these guys in. So now if this guy is 1/3, is the steady state probability of being here. Okay, and if you are here with half probability you go here, half probability you go here. So the probability of being here is 1/6. Do you see what I'm saying? It's bogus in one sense because in this case, this is a significant size of this matrix, this graph. But if this was like, 25 million nodes, I mean like 19 million nodes, and I'm adding a few more nodes in that I removed before, then I can make this approximation. So the PageRank I compute would not be the original PageRank that I would have computed, but it would work. Now, I would give extra credit to anybody who would tell me something like this we have done in this class beforehand. Something pretty much similar. It's highly analogous. Resettlement is no. Remember, connecting things across is the only way you live.
The Z
Otherwise-
matrix.
What?
The Z matrix.
No.
So,
Think outside PageRank. Yes.
in
Creating documents is worse.
What?
Creating documents is getting towards vectors
Dimensionality reduction.
Why is that?
because you're tossing out a whole bunch of relevant information to make it.
No,
IDF?
no, that's not the
IDF?
No,
is that authorities and house where you have?
no. I'm just sort of changing my view as to what should be the highest grade for this class. But go ahead. Please help me. Somebody. So basically, the point is,
I
the
know,
true page
I know,
rank for
I know,
this
I
is
know.
not, yes, go ahead.
When you do LT semantic analysis, you throw back documents that were not originally and you include them in the.
No.
Yeah,
So,
yeah, yeah.
Tell me carefully what you said. You are in the
When
general.
you use semantic analysis,
Mhm.
you do it on a matrix of original documents. Then when you add documents to the corpus, you don't redo semantic analysis, but you project those to the new.
Actually, it's not the documents, but the query. But you should get the credit. None of you came even close to LDA. So remember when you need to change your grade. Just come and tell me. But that's the case in point, right? Because the true way to compute the map of the query in the factor space is to have put the query along with the documents, done the LDA, done the LSI. Okay? But that would, essentially mean that for every query you're going to do LSI separately. That's just going to kill you. It's already killing you, and now it's going to kill you even more because for every query you go to that. Okay? Instead, you are hoping that just adding one more query is not going to change the entire spread of the data, so that the access are not going to change too much. So it's like, if the original fishes were like this, right? Adding one more fish hopefully would not change the primary access. But on the other hand, if I get to add like 10,000 more fish, I can add them like this. And now it's completely changed. But it's the same idea here. If you actually were to put these nodes in and compute the page rank, then the true page rank for these would not be 1/6. Okay? Furthermore, notice that all sorts of crazy things I'm doing here. 1/3 plus 1/3 plus 1/3, and then 1/6. So the probability is little more than 1 now. All of those fun things get to happen. But that's a way you can approximate. Okay? I couldn't read this, but that's, you have to reintroduce dangling nodes and compute their page rank in terms of their fans. This guy's fan is this. C was D's fan. Okay, because C was pointing to D. Okay, and sometimes actually it could have been the case that B also was pointing to D. That's okay too. Because then it's 1/3 for B, 1/3 for C, so 1/6 plus 1/6. D will be 1/3 now. Now notice that here the numbers are becoming significantly larger than 1, but had this part been much larger than 2, then it would have become significantly larger than 1. Okay? You're sort of assuming that the steady state is decided beforehand, and then these guys are not affecting the system too much. Yes?
So is this a special case then? Because if that's significantly larger, if you're cutting 2 nodes out, it's one thing. But if it's significantly larger, if you're cutting 6 million nodes out.
Yeah, except that each of these 6 million nodes might be in different places too. Okay? And also they may not all have very high probabilities. Okay? You may be a dangling node without being a highly important node. All we know is some of the dangling nodes are highly important nodes. Okay? Anyway, so that's kind of a neat trick that we tried. I don't know whether anybody does this. The only people who have to do PageRank is Google guys. Why do I need to care about it? Right? And so, but it's interesting from a approximation point of view. Sometimes you do approximations, because otherwise you can't compute the original quantities. Here is another idea, which is actually a more interesting idea, which is that, remember the way the PageRank definition, PageRank iteration was defined, and this sort of comes back to somebody was asking whether reduce must be after map or not. Okay, it's connected here. So the way the PageRank was defined, you start with M0, you compute M1. You start with M1, you compute M2. You start with M2, you compute M3 until R0, compute R1, R1 compute R2, R2 compute R3 until Rn and Rn minus 1 are not different enough. In which case you have reached a fixed point. Right? Now, it's as if somehow everybody's PageRank has to be taken to the second iteration before anybody's PageRank is taken to the third iteration. That's what I'm saying. Is that really important? Okay? And in fact, you can argue that, in fact, one of the ideas you can use is that some nodes' PageRank is updated more often than other nodes' PageRank. What you really would like to do is update the PageRank of the nodes that will eventually be more important. Because the losers, why do you need to know the difference between 10 power minus 19 PageRank and 10 power minus 19, 10 power minus 20 PageRank? Okay, so what I could say is, as I'm doing this, I might want to actually focus on the more important pages first. In fact, this actually makes sense because the normal way you talk about so remember R0, if you have pages 1 to n being 8 billion or so pages, okay, and PageRank is a vector, numbers here between 0 and 1. Okay, now suppose this is Rn minus 1 and this is Rn. One way you compute the distance between these is essentially to say, take the element-wise differences, take the max of those differences, and you say that is the distance. Do you see what I'm saying? That's basically L infinity now. Okay, and if you do that, in essence, who is going to affect that distance measure more? The guys who are more likely to be eventually important might have had less than their important measure in the previous iteration, and so the distance is becoming higher. So if you get the important guys to get to their eventual PageRank faster, then this convergence will occur faster. Okay, so all this is saying essentially is, this idea essentially says that update the nodes based on the important ones. And so first, in the beginning, everybody has the same steady state probability. And then after first iteration, then you get somebody has slightly higher probability than the others. The ones with higher probability, you update them more often. And if you do this, then, and if you count, if you look at the convergence rate, you see that convergence is better. The question is, who is the good guy, who is the bad guy in this? This has to be a good guy because this guy is converging to the lowest error much faster. This other guy does come to the lowest error but much later. And this is iteration by iteration. And this is important guys get asynchronous iteration. So the first idea is called synchronous iteration. That means everybody's PageRank is changed from one iteration to the next iteration to the next iteration. Whereas in this computation, somebody might have their PageRank as according to 15th iteration. Some other guys might have PageRank only according to 3rd iteration. Okay? Actually, in this case, as long as each node is updated infinitely often, then you are guaranteed, there is a theoretical proof that you will get the same PageRank that the original guy would have gotten. So this is actually theoretically valid. There is no real approximation here. And this is sort of prioritized in some other area, this is called prioritized updating, prioritized sweeping, where your current PageRank is used as the priority for deciding whether you get updated. Okay? And this way, by the way, one of the interesting things is this way you can do entire PageRank in place. You don't need to. In a normal way of thinking of PageRank is Rn minus 1, Rn. And then Rn, Rn plus 1, Rn plus 1, Rn plus 2. So you take the previous iteration, compute the next iteration. The way I am saying it, you change things in place. So you only need one vector ever. So the moment you recompute one guy's PageRank, you just change that number there. Okay, so that's another very interesting way in which you can improve the speed. Okay. Any questions? Yeah.
For the first iteration, or say for the first couple of iterations, you still need to load the entire 8 pages.
No, I mean all I'm saying is the basic idea is if you have only one vector in the beginning, all of them are ones. All of them are 1 over n. After one iteration, one full iteration, somebody will have a higher PageRank.
So for the first iteration,
It's not even necessary. All you can say is instead of thinking in terms of iteration to iteration, you can say which node should I update next. So I'll have in the beginning everybody's probability is 1 over n. So my heuristic for picking the node to update would be pick the node that's already important and then try to update it. And so in the beginning, all of them are equal. So, and break ties randomly.
Yeah, so the part where you're picking it up on the first iteration, I'm trying to find out how to do that.
All of them are equal, so anybody can be picked in the first one.
Oh.
The moment one guy has a slightly better rank than the other guys, then you start changing. Okay? Again, this is just, this idea actually is anybody in this class who has heard of mark-codation processes? Okay. If you did, it winds up being used there too. This is basically an idea of prioritized updating. Okay. I have a few more minutes, so maybe I can start introducing the next topic. Obviously, I can't do too much today, but we introduce it so that we can start thinking about it. Which is clustering. That's what I'm going to do today. I'm starting today. The point about this is clustering actually is one of the more classical topics, okay, in this course, okay. And of course, classical in computer science is sort of a iffy thing because computer science didn't exist. In 1900s, the word computer meant a human being who does calculations. Okay, so I thought this, essentially shows our predicament. These are Neanderthals, and the early archaeologists, when he found this, and he